I thank you very much, the organizers, for inviting me and allow me to present you most of my PhD work. I'm from the University in Basel. I'm working with Professor Marcus Moily. And today I will try to answer the same question that Professor Bombarelli just took, but from, I guess, from a different point of view. And then I structured this talk like, first I will do a quick introduction. Then also in this part, I will give you some motivation why we want to do this and put it in a bit in context. Then how we did to train the influence of training data. We choose a really challenging chemical problem. I hope you see it as I do. And then how to get better data through uncertainty. And I am a chemist, so I would like to relate this with what how the chemistry relates to these errors and to the data. And finally, I will draw some conclusions. So let's start by saying that this is a golden time for machine learning. You can achieve really huge, really nice accuracies. This was a dream in the 50s and in the 80s. But nowadays, you see, there's a bunch of models, but all of them need a lot of data. That's the first thing that jumps from this. If you have more data, you will have better results. That's the problem. Machine learning methods are really, really data hungry. And usually we keep creating larger and larger databases, thinking that it will give us better predictions, but there is something we must consider that is well known since the time of Charles Babbage. That if you have, it doesn't matter if you have a great model, if you put trash in, you will obtain trash. And the community in artificial intelligence has seen this before. So if you take a database that has a bias against minorities for classification problems, you will continue the cycle of discrimination. And usually what they suggest is, okay, if my model is discriminating against Asian people, I just add more Asian people to the training set. But we know in chemistry that's not easy, right? That implies a lot of time of calculation and a lot of expertise. So we know that data is a precious and limited resource, but more importantly, data is only as valuable as the insights we can get from it. So for companies, data is an asset, and bad data makes a lot of waste on time, money. And this is the point that I want to go also. The data generation implies money, time, resources, and it is also a large bottleneck for democratizing these methods. So nowadays, only researchers that have a lot of computer power can get to use these machine learning models. But if you don't have it, well, good luck. And also, the second point is, every time we generate data or we train a neural network model, we are producing CO2. So that increases the carbon footprint. Then if we have all of this in mind, we now want to do more, so keep the same better good predictions that we have with less data. And I would like to think of us, the machine learning community in chemistry, like this tale of the elephant of the blind people. We have now people that is working, creating wonderful models, more robust models, trying to incorporate physics, and everyone looks the same for different perspectives, but we all know there's an elephant in the room, the data, and we all know it is important, but there's not too much development still in that direction. So these motivate us to test how the influence on a real chemical problem is of the training database. And we choose this challenging problem because it implies a really small change in chemical structure. So we have tautomerization, that you make a migration of one hydrogen atom, but also the formation of a new double bond. And that implies, this is a nice example because both structures are chemically independent, and also the difference in energies between them is hard to compute. This problem is important for RNA, for drug discovery, a lot of things happen. So what we did, we take our homemade FISNet, it's a message pass neural network, and we tested the molecules on the Tautomers. We select Tautomers because there's a real life example. So there are reactions that were collected from literature, and there are a lot of them, and we can compute it quickly because they are up to some relatively reasonable number of atoms, I think 40. And we Now, want to evaluate two things. First, the chemical space. So for chemical space, we select QM9. All of you know it. It has its own bias. It's around 100,000 molecules. And it came from GDB17. And GDB17 also has some bias. Then PC9 was designed as a competition to QM9, and exactly with the idea of making it more chemically diverse. Then we create this ANI1E. ANI1E was basically the equilibrium structures of ANI1 computed just to an optimization and frequency calculation. We assure not imaginary frequencies, just for having the complete part, because we also want to compute how the conformational space, the sampling of conformational space with influence on these predictions. And then we have the two flavors of ANI. ANI1 that is 20 million molecules that is created with these 57,000 molecules I told you, doing normal mode sampling. And then ANI1X. ANI1X is created with an active learning strategy starting from ANI1. So it reduced 75% of the original molecules. And what we find is that, indeed, not surprised, data matters in the predictions, but also we can relate a bit these with the results. So first of all, we notice that ANI1X is the best performer because it has a good number of samples that were selected. But interesting things happen if you compare ANI1 and ANI-E. ANI1 is 20 million structures, but it's the worst among all the ones we test. And also, ANI1E is not that bad. If you compare it, it's performing more or less as good as QM9. But then we also have PC9. PC9 is performing very well because it is designed to cover a good part of chemical space. We also have in mind to see how much we can extrapolate. So all these databases are limited to top 9 heavy atoms, but what if we want to predict larger molecules from these small molecules? And what we see is that, okay, you can do it some reasonable. And this is a part where I remember of previous talk. These mean metrics hide a lot. And I think at some point that will be clear. So in the paper, I encourage you to read it. We tested many things, number of heavy atoms, specific, they call the number of one specific atom influence prediction, structural, and visualize. We also visualize a bit chemical space. But in this figure, I just want to attract your attention to the number of atoms that we have in the molecule. So the bars represent the samples that we have, and then is the mean absolute error in the prediction. And we see that for small molecules, there is always a large error. Why? Because the chemical space for small molecules is really reduced. So you might need to put the molecule in there to get it a good prediction. So the idea of going from large to small, it's a bit of a problem here. And also second part, if you look to the left, is that we test what is the influence of the number of heavy atoms in the prediction. And we find that you can still have chemical accuracy up to some point. That is interesting because we can start to notice where are the limits of our models. And after 25 atoms, I will say you start to have trash and things that are totally unreasonable. But also we didn't have too many molecules to test, so that's a problem. Some preliminary conclusions of this part. Results indicate that more data does not imply better predictions. That is kind of shocking because it's again common wisdom. But the quality of data can compensate the lack of it. So we see that ANI1 has a lot of data, but maybe it's not the best data, contains a lot of redundancies and contains a lot of things that go into the prediction. Also, an interesting part for me is that if you explore correctly conformational space, you can get around the lack of exploration of chemical space. How we notice this? Because if you look to the chemical space that is covered by PC9 and the chemical space covered by ANI1, they are different, but still ANI1X is performing better because it contains this accurate information about conformational space. In the left, I'm showing you this T-map plot that was made by my colleague Eric Beuter. Basically, he's projecting the molecules we test, and in this T-map that is based on similarity fingerprints, you notice that the red points are the molecules with larger error. So we can start to look to where are the problems in the prediction. So these kind of moieties are not very well sampled, therefore it will be complicated to predict it. And well, I think now I convince you, but before Professor Bombarelli did it, that training data matters. But how we get better data? It is challenging because we a priori don't know how. So the first thing that came us to our mind is how sure are we about our own predictions? And we need to quantify uncertainty. Uncertainty is the link between what is in the data and what we are obtaining. But it is problematic for neural networks because the usual approach involves this in panel C, an ensemble method. So you train many neural networks to obtain a mean and a variance. But if it's already expensive to train one neural network, imagine now training 5, 6, 8 until we obtain a reasonable value for variance, a reasonable value for mean. There, of course, are alternatives that Bayesian neural networks where you put a priori on top of the weights, but it was proved that they are also really computationally expensive and at some point become untrackable. So we focus on these deterministic methods that we are expecting by some hard statistical assumptions that we can recover the variance and that variance can be related to the error in the data. Then our approach was to use evidential deep learning. This evidential deep learning is based on assuming that we can describe the prior will be the normal inverse gamma distribution that I represent here in this 3D plot. And then the mean will be represented by a normal distribution, and then the variance will be represented by the normal inverse gamma distribution. Normal inverse gamma distribution, sorry. And it is nice because you only need to modify the last layer of FISNet. So we take FISNet, and usually FISNet returns only energies and charge per each atom. But in this case, it will return me also alpha, beta, and gamma, that are the parameters that I need to parameterize my distribution. We implemented this model in PyTorch. Soon it will be available in GitHub. Also, the preprint of this paper we submitted today, so most likely tomorrow you can look at it. And also it's important here that the loss function change. So now my loss function is computing one part, the negative log likelihood between the assumed distribution, and then we have another term that is correcting the parts that the distribution is describing correctly. I want you to focus your attention on the lambda parameter, because that lambda parameter is what it will more or less turn the variance of the uncertainty that we want to compute. So if you have too small value, that implies that the model is totally confident about what it's predicting. If you have too large, the model is totally afraid of what it's predicting, if we want to think of the model as a person. And this correction is just the mean absolute error of the normal L1. And the first step, and one of the problems of this, is calibration. Maybe you hear about it, but calibrating a neural network that can return us this, that the error can really relate it with the variance as we wanted to expect, is kind of complicated. And there are two flavors. One flavor is based on this variance. In this variance, we will like to, that for each of these values of variance, we can relate it directly with the means, the square error. So what we did was to code it in a number of pins, and then the number of pins we computed the road mean variance and the road mean square error. And well, that is not really good, but you see more or less some linear trends. Ideally, if it's correlated, it go in the diagonal. But we see that if you increase the data, there is also increasing dispersion. So there are some thresholds that you need to consider. A second flavor that is more typical, but I don't personally like it, is this interval bias calibration, where you are having a predicted number of molecules, so a predicted number of samples, and then you observe how many of those samples really correspond. And then you just compute the probability. In the limit of infinite, it should be 1. It should be also the diagonal, but this can be a bit misleading because we have some parts where it's predicting bad, where parts is predicting well. So we compute miscalibration area. And the sum of these two, we find that a value of 0.2, 0.4, 0.75 are more or less the best. And with that, we now have a model that is well trained. Now the thing is how that relates to chemistry. And to do that, we take QM9 again. QM9, it's biased. because of the natural enumeration, the way it was built. So we take a small part, 31 to 150 structures. Why? Because I want to have 25,000 molecules for training. And here I'm showing that in this T-map, again done by my colleague, that all the black points are ones I don't include, and the blue points are the bias. So I'm biasing towards some heterocyclic 5-member, 6-member. And then from this, I do a test train. For taking the test set, I randomly choose. This is the second part. And now I have my test results. And I have one T-map for mean square error and one T-map for variance. One problem that we find is that there is not a direct linear relationship between these two quantities. And that's problematic, because if we want to use this in active learning, that would be like the final end, we wanted to correlate those two quantities. But more or less, we see that the parts that are less samples of the extremes of the tree that show larger variance and also larger error. So let's see that we are doing well, more or less, in distribution. But also another way to look at this was by classifying my predictions. So what I did was too simple, just taking an energy cut that was the mean square error and the cut of the variance that was the mean variance. And then I create these 4 classes. If you notice, more of the models are true negatives. That means that it has a small error, a small variance. That's good. And also we have true positives, and true positives starts to increase with the value of lambda. As we said, lambda goes to increase the uncertainty. But the interesting questions come on false positives and false negatives, because in false positives, we see that it has a small error, but a large variance. What we find is that in this case, the molecule, or the model, has information about this molecule, but it has not too many. So it's a rare case. Therefore, it is not really happy, or it is not sure about the prediction. But the false negatives are the different question. In the false negatives, we have a large error, but a confident model. And this happens when you start to have conflicting information or noisy information. Because as I'm showing you this example here with train and test, in train I have this 7-member ring. Maybe this is not realistic in chemistry, but this is what is in QM9. And I have a test molecule. You see the difference is really tiny. It's just the movement of the double bond. But it turns out that in QM9, or the part where we take it, that is not really typical to find 7-member rings. Therefore, it does not have an example of a 7-member ring with the position of the bond. And we're having problems. And we can also track that to the rest of the molecules. And we see more or less how the composition starts to relate it with the variance and the error, and in which case, and that we need to find a threshold between how much information we have and how much information we need. So, final real example, because I'm also running out of time, we take the embedding. So, as I said, FISNet is a message pass neural network that has 2 parts to encode the molecules. One is a radial-based function layer and embedding layer. The radial-based function layer, what I basically took is each molecule, I took the pairwise distance between them and then average it with all the molecules with the same size. And try to correlate if there is a trend between the error and the mean distance. And if you see there's more or less somehow center trend, also the distance between the molecules and the test molecules are center. So we see that this metric is a bit misleading. Why? Because I only consider molecules of the same size with the same number of atoms, because the matrices then can be compared. But I'm not seeing the influence of other molecules. So that gives place to larger errors because of extra information that is creating only noise that I'm not quantifying. Then another way to visualize this is with this polar plot that I'm showing you on the left. Polar plot, basically I take a molecule and then I'm computing the pairwise distance between each of these molecules that are showing there. The molecules are in the train set. And what we find is that basically we wanted to predict this molecule with the nitrogen and hydroxy group with the molecules that you see there. They are the 10 closest molecules in the embedding space. So you see, well, there's some information, right? There is one OH over there. There is a nitrogen double bond in a ring, but I don't think it's enough information. Also, in another case that I don't put it, if I have too much information, I will find that I have a large variance, but a small error. So we need some threshold. So to conclude, more data does not necessarily imply better data. I hope I convinced you of this. What we needed is more like a specific data or concise data. That the uncertainty quantification, it can be a good way to find how to get better data. But still, I think that uncertainty and error does not correlate, so that's a problem. And well, we're still missing a quantity to quantify information. And this is an important part because, as some of the previous speakers mentioned, if you took these mean metrics, it hides a lot of information. So it looks like it's all good, but if you go to particular examples, you start to see the problems. And that's, I think, one of the cores of machine learning. Having too much data hides you of details. So what we'll think to do next is connecting generative models and regression models. So using a bit of these generative models to create the information that is missing on the fly. And finally, well, as my friend Drake shows, I think better data is the option, right? So with that, I would like to thank you for hearing me, and to my collaborator, Professor Max Moily, Eric Boitier, and the Swiss National Foundation for Money. And that's my mail. So if you have any questions, I will be happy to answer it.
Thank you very much. You highlight the issue of data quality, but what do you think about putting more sort of inductive biases or equivariance and so on to compensate for the lack of good data?
Well, I have to say I don't know too much about equivariance and how can be the influence on that, but I am assuming that maybe also we can gain a lot from that. But I will lie to you, I don't know very much about it.
Thank you.
Thank you so much for the talk. You mentioned the quantification of the information. Did you consider using the information entropy based on the probability?
Yes, we did that on our first paper using the Kullback-Leibler divergency between the bound distances. I didn't add those results because that opened another can. Problem is that it is not so easy because you need to know a target. So you need to know before to start what are the distribution that you want to have. So what we have in mind is, okay, I have something to start. How much? So how can I get better data? So reducing or increasing? So the problem is very much is that we need to know by starting the information of the test. And that sometimes is not an easy task.
You're talking about this if you're doing the regression task, right? Mm-hmm. For the if you bring your model to the classification task and try to build the based on the uniform data set, which has the maximum information, mm-hmm. that can be one of the ways to do it. If you're interested, we can talk because I have done it and it shows very interesting results.
Yeah, that would be really nice. Thank you.
Can we get Jose to come up and start setting up as we take another question? Oh, yes.
Great work. Quick question. Doesn't it imply that we should go back to the roots, what cheminformatics people been doing a long time ago? Just compute fragments, enumerate all of them, and call it a day?
Well, yeah, that's maybe the Ammons approach. That is like you find the different. So yeah, that's more or less what the Ammons approach will do, right? So you compute up to the parts of the molecules and then you try to get it better from there. My problem with the Ammons is that you need larger and larger Ammons to get better results. And I'm not sure if we can also do Ammons in combination with less data, less redundancies. But well, that's a nice point to explore.
Any other questions? I had just one question to follow up on that. I mean, does it mean we need another definition of molecular similarity that says something about how much similar information is provided for these tasks that could be trained, like to identify compounds that are similar or not similar, and in generating these data sets?
Yeah, absolutely. That's also one of my thoughts. We need a better way to quantify how molecules are similar between them, and more importantly, how much information they have. And that's something I go unraveling around my mind, but still cannot come with something. But yeah, also the metrics of current metrics, it depends on how you define it, right? And it's problematic from design, but that's a whole work to explore. We can talk more about that.
Any other questions? If not, let's thank Luis.